Me too. Do all the quizzes again.
It's the devil. That's why I promised myself I would do it.
Everything just turned around. Yeah, I had a statistics test I didn't know about. My day.
That's not a good feeling.
Found out about it yesterday. So I didn't do homework last night for this class. I was doing a take-home test for that class. Found out about. Because Firefox doesn't display all the changes to our announcements anymore. So I just found out that changed. Now I just use some of the browsers.
All right. Hi. Pressure vessels. Pressure vessels allow you to barbecue. Pressure vessels allow you to make boilers. You see pressure vessels in lots of places. A hydraulic cylinder is a pressure vessel. So there's lots of applications of pressure vessels, and this week's lab is on pressure vessels. We're going to take a couple of those things. What are those things that we stick on things that measure how much they stretch?
Strain gauges.
Strain gauges. We're going to take a couple strain gauges, slap them on the side of a pressure vessel, blow it up like a balloon, measure it, see what happens. So the point of today's lecture is giving you the fundamentals to understand what's going on in tomorrow's lab. So if you take a balloon, and that's maybe a little easier to visualize, if you take a balloon and blow it up, what's happening? You've got pressure that is stretching it sort of equally, because that's what fluids do. And I know that word's a bad word right now from a lot of you, fluids. Just the glazed looks on the faces. This fluids project. I'm going to have to get Feller. Anyway. So it makes things stretch in this direction and this direction, essentially hydrostatically, evenly in all directions. And we're going to learn how to connect some math to that by thinking first about this cylindrical, capped in, I don't know, like a hot dog, like a capsule, whatever you want to say. And we're going to do a statics problem on this guy. What do? We need to set up a coordinate system first. And we're going to set up a coordinate system that's got a x direction along that away, and we got a y direction along that away. And in terms of the pressure vessel itself, we also can call this the axial direction, which makes sense according to what the terminology we've used all along. The new one is that this is called the hoop direction. And so if you took your pressure vessel and rotated it, essentially you have to think about slapping this coordinate system on the outside so that that y-axis is sort of tangent to the surface, so that any way you spun it, that y-axis would be along the circumferential direction. So that's our coordinate system, axial direction, hoop direction. And what do we have to always do to do a statics problem, or I guess we don't always have to do, but we basically take a section cut and we're going to look at the force balance. So our force balance, if we chop our pressure vessel, why isn't that doing anything? There we go. So our x direction is along it, and our y
direction is crossways. And what's a stress? That's just plain old definition of stress.
a force distributed over some area. What's a pressure? It's a force distributed over an area. Just it's a fluid doing it instead of weights in a lab or your hand or whatever. So if I want to do a statics problem, what do I need to balance? You do the sum of the forces. So we need forces, not pressures. How do we get forces? We multiply pressures or stresses times area. So that's how we're setting this up. We chop it in half. We have an applied pressure that has a value P. And that is, if I chop this thing in this direction, parallel to my x direction, what's the area that the fluid, that the air is acting over? It's the area of the circle. It's just a pi r squared. So the force on this side, force due to air, is our pressure times, and this area is pi r squared. So it's that times, get out of there. Oh no. What are you doing? It is, what am I trying to say? The force is the pressure times the area. Force is the pressure times the area. All right, so what's resisting that? If I chop that in half and that's my pressure going one way, what's resisting it? What's my balance in the minus direction? It's the stress distributed over that flat face, the cut face. So that's what these arrows are. That is the stress distributed over that. And what's that area of that flat face? It's the circumference times the wall thickness. So the circumference 2 pi r times the wall thickness t is the area of the actual metal cut face. And so the force on this side is the pressure. No, it's not the pressure. It's the axial stress times this 2 pi RT. Okay, so in the one way, you've got the fluid exerting pressure over the whole face. That isn't a face, it's empty space. And resisting that, you've got the stress distributed over the surface area of the vessel material. And that's all we got going on. That's our sum of the forces in X. So we've got plus pressure times pi r squared, and we've got minus axial stress times 2 pi RT.
Would you say that this is reactionary force from the other one?
This guy?
Yeah.
Yes. So yeah, the big arrow is like the equivalent force of the pressure. So we've got all this resultant force of the pressure that wants to head this way, counteracting that. You've got the stress in the shell itself. That's our equilibrium balance. Pressure in one way, stress in the other. Multiply those by the respective areas. All right. Multiply those by the respective areas, and you get this, and we can, that is equal to 0 because we were still doing a statics problem. And we can solve this guy out for axial stress. And that ends up being this guy over this guy, 2 pi RT. All right, so pi's go away. That squared goes away, and that guy goes away.
Is that
2 pi r is the circumference,
okay?
and the thickness is, the T is the wall thickness. So that's area of the metal part.
Pi over 4 times d1 minus d naught squared.
Yes. That should get you to the same place. That should get you to the same place. what am I doing? PR over 2T is what that simplifies to. So this is our axial stress in the wall of the pressure vessel is a function of the pressure, how round the pressure vessel is, and twice the wall thickness. Those are the things that matter in terms of how much stress is developed in the wall of the vessel. All right, cool. We have another direction. We got to slice it the other way. And I don't know why that's there. There we go. So now we slice this way, and let's say we have an arbitrary dimension that we're going to call the W this away. What would this dimension be? It's the diameter, otherwise known as 2 times the radius. So this guy is 2r. All right. So if we do the same sort of formulation, what would be the force because of the hydrostatic pressure this way? It's the pressure times 2RW. So force times area. No, pressure times area is the force. And how about this guy? If we have our wall thickness that we call T, and it's still the same W this away, we must have this hoop stress is this direction times WT is the area of one of them, but I've got 2 of them. All right, depending on where you see this, you may also see this guy referred to as a sigma sub theta because it's in the around that radial direction, or circumferential. So this may also AKA sigma sub theta. All right, so we can do the same thing. This is my sum of the forces in Y is plus this guy minus this guy. And I can solve for this guy is going to be this guy. Whoa, I lost somebody. There he is. Over 2WT. We can do a little more canceling. That guy goes away, that guy goes away, that guy goes away, that guy goes PR over T. Did I lose something? PR2W, 2RW.
Does it matter what goes?
No,
Okay, cool.
especially since he goes away. 2WT. So we end up with what fact does this tell us? This tells us that if this guy is PR over 2T, and this guy is PR over T, that tells us that our hoop stress is twice as much as our axial stress. So if you have a cylindrical pressure vessel, this guy is always 2 times that guy. It's just the way it works. So what is this implying? This is saying hoop stress is 2x axial stress. So, okay, that's not necessarily a good thing, or that means that you might need to make considerations for that, that hoop direction, which we'll talk about shortly. What if instead of a cylinder shape, we do a spherical pressure vessel? Okay? The same math is going to work. And if I chop it along any diameter, and I call this my x direction, I hope you can follow that my sum of the forces in the x direction is going to give me exactly the same math as my axial case. So I know I can kind of jump forward to the answer, and I can say my sigma x is PR over 2t. But it's spherical, so no matter which way I slice it, the sigma is PR over 2t for a spherical case. Spherical pressure vessels are better at being pressure vessels than cylinders. They're just a little harder to build and a little harder to deal with because you wouldn't want your barbecue gas rolling down the hill. No, whatever. But they are much harder to manufacture a nice sphere. So from a practical standpoint, it's easy for metallurgists to make a hot dog, and it's hard for them to make a bubble. So what do we do with that? You can wrap it to make the walls thicker in this direction with simply more material. You can augment with carbon fiber. You can do a lot of things to make it better. Have any of you ever actually been on a submarine? No. No submarines. Okay. What else is another... I can't even think of another example. But you don't... yes, but you don't usually get to see the ribbing that I'm talking about. Well, then there you go. And so you've seen the fact that there is support ribbing to make it stronger in that axial direction. So you either change the structure of the wall, you wrap the outside of the wall, you do something to account for the fact that that poop direction is sees that factor of 2 more stress. So that's the scoop with that. All right.
Why is it 2 times?
Because it... That's...
The math worked out, but why?
Because the math works out that way. Because of the geometry that you've got, the way the forces distribute, when you've got the circumferential slice versus spreading things out over that hemisphere shape as opposed to a planar shape, and yeah, the math, that's just how the math works out. It's nice and tidy like that. Because statics said so. Not because your mother said so, but because statics said so. All right. We got a problem. We got a problem. We got a problem. Tomorrow in lab, what's the thing that you're going to use to measure? Strain gauge. What does a strain gauge measure? It measures strain. What did I do? It does. That's all it knows how to do. It measures strain. So what did I just derive stuff for? Stresses. All right. What do we know in our clever brains? How do we relate stress and strain? Hooke's law. That's right. What is Hooke's law? Stress is the modulus times the strain. What was one of those assumptions that we had to make that this is going to work?
Linear, something to do with the displacement.
Something kind of, sort of, maybe. One direction only. What happens when you blow up the balloon? You've got things going on in X and Y. We are now no longer dealing with uniaxial stresses. We are dealing with planes, planar, or biaxial stresses. So if I have this structure and I pull on it with an axial load, what happens? Hooke's law is true. I pull on it with some force P, F, whatever you want to call it. It gets longer this way. What happens the other way? It gets shorter. What dictates that? Poisson's ratio. But what happens if I'm pulling on it this way too? Yo no sé. Tengo un problema. We need more equations. So, here we go. Huh? We need more equations. We need more cowbell.
Well, I have a quick question.
Uh-oh.
So, when this...
He's back on this 2T thing.
No, I'm over it. So, if we were to look at a pressure vessel and if we were to, like, cut off the hemispheres,
Mm-hmm.
and we've got this cylinder, pressure is going to act in all directions normally.
Right, because that's what pressure knows how to do.
And for the hemisphere, the force is going to act like through the whole thing.
Right.
So you're going to have an X component and a Y component.
That's right.
So your stress is going to be acting in both the X and the Y.
Right, but in our force balance, what do? We only talk about the X direction or the Y direction. So it still resolves out. But yes, because of that hemispherical shape, it's not just in the X direction. Sure, that's absolutely true. Okay. Wow. All right. So if we have a thing and we apply a stress in a given direction, we expect, we know, we understand that it's going to get longer this way and shorter that way. That's what's going to happen. What are the equations that, as far as we know, govern that? We know that the strain in the X direction, and this is just Hooke's law, going with what we know so far, we know that the strain in the X direction is 1 over the modulus times the stress. I just solved this guy for strain instead. Same equation. Okay? What do we know about the strain in Y for this situation? That's related by Hooke's law. Okay, so that is minus, not Hooke's law, Poisson's ratio. So minus nu times the strain in X. This is brushing off a little bit of cobwebs, but now if the stress in X is this thing, I can say that the strain in Y, my epsilon sub Y, has to be minus nu over modulus times X stress. All right, all with me on that one? No big deal? Good? Okay. Now, what about, riddle me this, Batman. I got some sigma y. I know that if I do this in isolation, what's going to happen? It's going to get longer this way and shorter the other way. And what are the equations that are going to govern that? I'm going to get some strain in the y direction that is 1 over the modulus times the stress in the y direction. That's my plain old vanilla Hooke's law. And I know that my strain in the x direction, because of the y loading, is the negative of Poisson's ratio times the strain in y, or minus nu over E sigma y. Now, we've also got in there, and boy, we only used him like once. There's this shear strain and shear stress relationship that is the shear version of Hooke's law. What was that one? That the shear stress equals the shear modulus. Oh, yeah, that's vaguely familiar. So shear stress, and there's that shear modulus in there. Now, all of these I have solved in terms of strains, so I'm just going to solve this guy in terms of strain so that it's analogous. So I've got everything in terms of strains. All right. Now I'm going to rewrite these guys. I'm going to scoot him over a little bit and make him a little bit smaller. All right. So I'm going to rewrite these equations in a slightly different form. I'm going to say my strain in X is equal to one over the modulus times the stress in X, but also, what else? It is equal to nothing and nothing. I can rewrite the second one as minus nu over E sigma X and nothing and nothing. Then I've got these other two equations. Bear with me. That are not in terms of sigma X, but they are in terms of sigma Y. This is a system of linear equations. It's a system of independent linear equations that I can just add them up. I can just add them up. So I then get that this guy is equal to 1 over E sigma X minus nu over E sigma Y plus no tau. Okay, so that's just adding the first. One of those needs a Y. Who needs a Y? That guy needs a Y. So that's adding the first and the third lines. And then if I add the second and fourth, I get minus nu over E sigma X plus 1 over E sigma Y plus no tau XY. Ooh, I got some squints. You following me? Okay, let me see if I can help with some color here. Okay, this is just that. Okay, the one that's circled in red on this side is just the one circled on that side. I just added these extra terms that are zeros. I mean, I could say it's also equal to 0 times Cassiola's bank balance. It's just 0. So, that doesn't mean your bank balance is 0. But 0 times it is still 0. So, this guy is this guy. You got it, Brogdon? If this guy is here, and this guy, maybe that's backwards.
On the left, I think the bottom one's.
Yeah, I think you're right. Let's see. We have sigma Y is the 1 over, this guy. Yeah, I'm making a mess of it. This guy is Y. And that guy is X.
The last two
The last two are the same. The last two work. But so that guy, 1 and 4. So the one with the goofy looking star is really that one. Wow.
From the Poisson ratio?
Yep.
Is that the C symbol? It's supposed to be over there and the other.
This is gamma.
All right. Sorry. Making sure.
That is new.
Oh. Yeah.
All right. So now that we've bogged down on subscripts and I've horribly confused people, we have a system of equations that is in terms of x strain, y strain, x stress, y stress, and shear stress, and then we got this guy floating over here that is also shear strain. Does anybody see a matrix in the future?
Actually, it's beautiful. Is it 2 by 3?
No?
What's next?
3 by 3. We got 3 kinds of strains. So we have strain X, strain Y, and strain shear. It's magic electrical paper. Gamma sub XY is your shear strain. All right. And I have a vector of stresses here. And I got an empty box that I need to fill in here. And based on this gobbledygook I've got over here on this other page, based on these guys and the fact that gamma xy equals 1 over g tau xy. I'm struggling, y'all. Worse than normal. There we go. We're going to put those 3 equations into this matrix over here. And what is that going to look like? That is going to look like a 1, that's going to look like a 1 over E, a minus nu over E, and a 0, and minus nu over E, plus 1 over E, and 0. And what's the last row? 0, 1 over G. That is the matrix for biaxial stress. It's the relationship between stresses and strains in 2 dimensions. Woo! Oh boy. Now, what are those things that we're going to stick on the pressure vessel and measure with? So, okay, the way this is set up, this is my input. These are material properties that I know. So this is set up as my answer, my output. But what are we going to record tomorrow? So guess what we got to do? We got to work backwards. Oh. Okay, but wait a minute. You have tools to do a matrix inverse, right? No big deal. Yes, you do. Yes, you do. Yes, you do. But even better, actually, look at what's going on here. You perhaps have heard the term of uncoupled equations. Maybe you have, maybe you haven't. This right here is an elegant example of what it means. Does this line have anything to do? Does this number depend on X or Y normal stress? No. This line is uncoupled, is decoupled from the rest of it. That's what that means. It ain't got nothing to do with it. This line ain't got nothing to do with these two lines. These two lines got nothing to do with this one. So they are independent. They are decoupled. Which means, although it's a little bit ugly, you can explicitly solve these the other direction. You can do the algebra and we can get math. Don't make that face because I'm going to give you the answer. I saw that. Where's the answer? Crap.
You do have to solve for it now.
Yes, now you have to do that math. Rawr. Nope, there it is. So the answer, the analytic solution that we're going to be able to use is that, where did they go? I did leave a page.
Okay, we'll give you an extension.
I did. I lost a page between this morning and this afternoon. All right, by memory. We end up with 1 minus nu squared is the coefficient, and then we have a strain. The x one is x plus nu y. I don't know. I don't believe I trust my memory.
Can you just pull it up on
I can, and I will, because this first thing is a sigma. Yes. Yes, it's a new Greek alphabet.
Is that the Ryan symbol?
Yes, it is kind of like the artist formerly known as. I am the professor formerly known as. That's my new symbol. I really cannot believe that I did that. All right. I think I have an even quicker way to get to it. Yes, in fact. Wait. Ooh, it went away. Unable to connect to the internet? Really? Really?
It's just must be on.
It's Monday. It's Monday. It has been Monday all week, this week, and last week.
Does that mean next week will be Tuesday all week?
Yes. Yes, that is what it means. All right. Yeah, okay, so modulus over 1 minus nu squared. Where did that go? Why isn't this showing anything to you? What's going on here?
We might have to use this other screen.
Output to clone. Right.
We'll all crowd around the screen.
Where did it go? There we go. There they are. There they are. Did I have a 1 here instead of a 1? Okay.
And you did have a name.
So the only thing I missed was the fact that the whole thing needed to be multiplied by the modulus.
Yeah.
Okay, that's not too bad. All right. So, and let me. So it's the thing in the box that you need. So modulus over 1 minus nu squared. Pay attention to your subscripts. Pay attention to your subscripts. Now, this is not going to let me write on it.
Is that a gamma on the second line?
No.
It's a new.
No, he's a new. sort of looking like he wants to be a gamma, but he's not.
Just double check.
Yep. Oh, that's wise to double check my scribbling. Y'all should know that by now. Yes, ma'am.
So instead of doing the 3 by 3 matrix, so have we just done the 2 by 2 and solved through sigma x and sigma y?
That's what this is. That's saying, I mean, if you do the math, that's what you get. Because they're decoupled, it reduces to a 2 by 2 that you can then just solve. All right. So, is this thing? No, it's not one of the fancy ones. Okay, I'm just going to point. Which, if I have my x and y direction, remember from our coordinate system that we stuck on our pressure vessel, which one is our hoop? Y. Hoop is y. So in your little notes right there, go in here and put hoop by the y's. And put, what's the thing? Axial by the x's. So tomorrow we're going to measure hoop and axial strains, and these two equations will allow us to calculate hoop and axial stresses. All right? Y'all all got that situated? Okay, so I do want to do one problem that's sort of a forward problem, saying here is the stress. What are the strains? Now watch, it's going to goof up again. Of course. Come on. All right. Wow. All right. So now we got our equations. Hey, I can fix him. E. All right. So we've got an example. What are the stresses and strains in the walls of a cylindrical 10-inch diameter steel vessel that is pressurized to 500 psi? Use 30 million psi modulus and 0.3 for the Poisson's ratio. So what do we know? We know that P equals 500. What do we need to know? We have that our axial stress, what's our formula? PR over 2T. We know our hoop stress is PR over T, or otherwise known as 2 times our axial. So we need our radius. We are given the diameter is 10, our radius is 5. What else are we given? We're given that the thickness is 0.0747, which, by the way, is the actual thickness for a 14-gauge steel. Random trivia. All right. 0.0747 PR over 2T. What do we got? 500 PSI times 5 times 2 times 0.0747. This is 16,733. And so therefore this guy is 33,467 PSI. That's the forward problem. That's given this situation. Those are the stresses you expect in the wall. Hoop direction is around it. Axial direction is along it. What do we want to know now? We want to know strain. So for axial strain, which equation is that? That is strain in X is equal to 1 over the modulus stress in X minus Poisson's ratio over the modulus times Y stress. And we sub in numbers, or actually we do a little bit more math and pull out the 1 over E, axial minus nu hoop. Notice I just changed my subscripts, X and Y, axial and hoop, equals 1 over 30 million times 16,733 minus 0.3 times 33467. Axial strain is 0.000223. Stephanie. Hi.
Hi.
What's the units on strain? They do not exist.
Yeah, that's almost like, is this a trick question?
Yes, yes it is. I don't know. The same reason I referred to Cassiola's bank balance. I have no idea. Because it's the 14th week of the semester and we're all going a little boop boop. For hoop stress. No, hoop strain. Hoop strain, that is my Y direction, 1 over the modulus, sigma Y minus nu sigma X, or 1 over E sigma hoop minus nu sigma axial. By any case, 30 million times the bigger number minus Poisson's ratio times the smaller number, .000948. So to summarize, the stresses in the hoop direction was 33,500 or so. In the axial direction was 16,700, and the strain, what is that? That is the same as saying that, right? And what is that? You remember what those blue boxes read out in? Microstrain. So this is 223 microstrain. And the axial is 948 times 10 to the minus 6, which is also 948 microstrain. There you have it. And we didn't get to talk about thick wall pressure vessels, but there is already there is a Tegrity recording of the thick walled pressure vessel stuff. So there you go. It is good perspective, and it will not be explicitly tested. So, all right.